Let's learn how to use the convolution method to solve a differential equation quickly. So we're going to look at this problem. So let's say we have solved y to the fifth derivative, y to the fourth derivative equal for e to the 3t with the initial conditions y 0, y prime 0, y double prime 0, y triple prime 0, all of them are 0, and y the fourth derivative evaluated at 0 equal to 1. So if you have a problem like that, what we normally do is we just assume the ys as the Laplace transform yt is a solution. And then what we do, we take the Laplace transform of the differential equation, both sides. So taking the Laplace transform, what will happen, we get this for the first term, because the fifth derivative. So that means you can start with the fifth power. And you know that all the other terms have a negative sign. So that's what you get from the first term. And similarly, from the second term, we get this one. So now we have the fourth power. So that means we can start with the fourth power here. Fourth derivative. So it can be fourth power here. And all the other terms have a negative sign. And then on the other side, you can see it is 4e to the 3t. So it is 4 1 over s minus 3. So we have on the left side, on the right side, we have 4 over s minus 3. Because when you have a e to the term, you just subtract that number from the denominator. That's how we do. Okay, now what we do, we're going to use the initial conditions as we have. So you can see all the y0 and all the first three derivatives are 0. So that means all of these terms going to be 0. So they are all going to be 0. And then even the third one. And then in the bottom, you can see these are all 0. And so only term that you get is, and this one also 0. So only term that you get is the fourth derivative, which is equal to 1. So when you move to the other side, you're going to get this one. So you can see we have s to the uh, fifth power plus s to the fourth power times ys. On the other side, when you move the y to the fourth term to the other side, you get 1 plus we have 4 over s minus 3. So that's what we have. Now the question is, what are you going to do next? So there is a problem many students do. There's a mistake actually. So what they do, they just leave it like that, and then we try to divide both sides by this factor. But instead, uh, I mean that step is okay if you know how to find the inverse of those on directly. But when it is like a partial fraction type of problem, it would be better to simplify this fraction. So we can simplify this fraction. So we take the common denominator. So when you take the common denominator, what will happen is you get s minus 3 plus 4. That means s minus 3 plus 4 means the numerator is going to be s plus 1 and divided by s minus 3. And that's what you get. So we normally do that when you have a complicated fraction rather than an easy one, because you can see when you divide by s5 plus s4, you can directly find the two of the partial fraction. So it would be better to like simplify it like this. Now what we do, we divide both sides by the s5 plus s to the 4. So we get this one now. So after dividing, we have ys equal, it is 1 over. So you can see this is s to the fifth power and s to the fourth power, and on the other fraction you have s plus 1 over s minus 3. Now what we can do is you can actually factor the first one. So when you factor the first one, you can see you can pull s to the 4 out. Then you get s plus 1 and then s plus 1 over s minus 3. And you can see this factor get cancelled out. So it simplifies actually a little bit better now. So you're going to get 1 over s to the fourth times s minus 3. And then what we're going to do, normally like if you get something like that, what we normally do is we use the partial fraction method. That's like a normal trick to do that. So we can use the partial fraction method. And if you need to know more about partial fraction method, then you can find there's a link in the description that talk about how to do those kind of things like very quickly, because there are special type of partial fractions that we use for Laplace transforms. Okay, so so let's see how to use this new idea. So what we can do, so then what we normally need to do is find the inverse. So that means you can see, so taking the inverse, so you can write this one as, so taking the inverse Laplace transform, you can write yt, which is going to be the inverse of that. So which is inverse of what we have is 1 over s4 s minus 3. Now what we can do, actually we can write this as a product. So what we can do, we can write this one as L inverse, the first one, which is s to the 4, and you remember when you have s term, this is actually closely related to the t cube. So that's the term t cube. But when you have t cube, we know that if you take the Laplace transform, you get the factorial 3. So you get the factorial 3. So we're going to put it there. But just to cancel that, factorial 3 means 6. We can write 1 over 6 outside so that they cancel each other. So we're going to manipulate the term like that. For the next term, we just leave it s minus 3. Because you know that s minus 3 is the Laplace transform of e to the 3t. So we already know that, e to the 3t. I mean, we already have the two terms. And then we know that when you have a product like that, we can use the convolution theorem. So what the convolution theorem says is that this answer is simply going to be 1/6 as a constant of the convolution of the t3, convolution we normally do star notation, and e to the 3t. So in the convolution domain, we already have the answer. So that's the answer in the convolution domain. So we normally don't leave the answer like that. What we do next is we just try to evaluate the convolution. So we're going to use the definition and we write the convolution. So that means we, by the definition of the convolution, we can write this one as 1 over 6, the integral from 0 to t. And then we know that, like, we do special tricks when we use, because we know that when you do the convolution, there are two options, because convolution is this defined like this. So it is f star g equals 0 to t f tau g t minus tau. So the question is, which one we're going to put t minus tau? Because the idea is you're going to put t minus tau so that it is easy to integrate. So in this case, what we normally do, because we have like a larger power here, because of that, we're going to put the t minus tau to the exponential function. So that's the idea. So if you do that, this is what you get. That means it's going to be tau cube in this case. And then e to the 3, you can replace t by t minus tau, d tau. So that's what we get. And then the question is how to evaluate this one. The trick is to pull out this term out of the integral, because it's independent of the variable tau. So we're going to pull it out and then we use the integration by parts. So let's do that part next. So we're going to pull out e to the 3 t term. So that means we can write this one as e to the 3t divided by 6, and then we have rest, we have 0 to t tau cube e to the negative 3 tau d tau. So what we do next, how to integrate this one? So we can use the di shortcut for this one. So the di shortcut, and if you don't know what is the di method, then you can also find that in the link in the description. So we use the tau cube to the derivative part, e to the negative 3 tau to the integral part. So we take the derivative of the first one, so which is 3 tau squared, and integral of this one is just divided by the constant. That's how we normally do. So that means it's going to be negative third e to the negative 3 tau. Keep taking derivative, so it's going to be 6 tau. And then here it is 1 over 9 e to the negative 3 tau. And then we're going to get 6. And it's going to be negative 1 over 27 e to the negative 3 tau. And then we get 0. So we're done on this side. That means here is going to be 1 over 81 e to the negative 3 tau. And then what we do, we can multiply across the diagonals. The first one is with the plus sign, the minus sign, plus sign and a minus sign. So that means we can write the answer now using the table. So we're going to multiply across the diagonal like that and add them. So that means if you write all of them, we get this one. And we can evaluate this as t and 0. So if you evaluate at t and 0, and you can see when you plug in 0, you're going to get e to the 3t over 81. When you plug in 0, we evaluate the bottom one first because of the negative sign. So you get the positive one now, and then the rest of the terms, and you can see all the other terms are going to be 0 because of if you plug in 0, there's a tau term. And if you plug in t now, and then we also multiply by e to the 3t. So what you're going to cancel all the negative terms because of that one. So you're going to get this one as the answer. So so this is the solution to the problem. So this is yt. And you can see you can get this answer actually just by a simple integration process. You completely avoid partial fractions. But just imagine, like, if you try to use the partial fraction method, this is what you get. So so what we have was we had a 1 over s to the 4th power, and then we have s minus 3. So to get, so that means if you write the partial fractions, you're going to get a over s, because you know that you have to write all the terms, and then b over s squared, and then c over s cubed, and then d over s to the 4th, and also we have one more, e over s minus 3, and you can see there are 5 unknown. This is kind of very interesting. So they have 5 unknown. So that means you need to find all five of them. So and it will be very complicated because you can even use the cover-up method for this one. Well, the cover-up method only works for the largest one. So you can find E and D is the cover-up method, but you cannot find the rest of them. That means you have to use the coefficients and expand them and do all of them. So and then also how to solve it. It's like you get 3 unknown here. If you write a general one, you have 5 unknown there. So it's going to take like very time consuming, but you can see you can avoid all of them just by using the convolution technique. So it's like a very powerful argument, and you can solve many problems using this method. So now you can actually try these 3 problems as practice problems, and so you can get familiarized with this one. Okay, so let's do them now. So let's solve the following initial value problems. So as the first one, we have this. And as a second one, you can try this one. So we have y double prime minus y equal t plus 1 with y0 equal y prime 0 equals 0. So you can try these 2 problems and you can see how well it simplifies, and you can use the convolution method to get the answer very quickly. And if you know the answer to any of them, you can discuss those questions in the comment section, and I can also provide some feedback for that. And also yeah, so you can discuss these questions. Thank you.